So good afternoon. Thank you for coming back. It's a long time. It's probably longer for you than for me because I get to stand up in front and get excited, and you have to sit there and listen. So thank you for coming back. You don't need a review after a few minutes, but I'll still give you a bit. So I told you that whenever you get confused, think of this classical picture of an atom in the presence of a laser field. The laser field ionizing the atom. You can almost think of it classically. Classically, it would take the electron a bit of time to find a hole and things like that. So you wouldn't get much different results. And depending on when the electron came over the lip and started to move in the laser field predominantly, it would follow different trajectories. If it's born at the optimum time, it goes along a trajectory that brings it back to recollide with the ion. There you see it there in that picture. And with the maximum energy in the problem. And so that would come in with some energy. I just said 300 electron volts here. I think I had a higher value earlier. I just made it up. It depends on the F equals ma, the wavelength and the field involved in the problem, but this could be a typical number. And when it recombines, it gives out photon energy, and that said 300 eV. If it's born a little later in the field, its trajectory will bring it back earlier, and it will have less energy. And if it's born later still, it will come back still earlier and still have less energy. So we create naturally a chirped pulse, radiations going from red to green to blue, in an orderly fashion, organized by the laser field, and in principle, that chirp can be taken out. So if we could go from 10 eV to 300 eV and remove the chirp, I don't know what the pulse duration is, I didn't work it out, but it would be only 10 attoseconds or maybe 20, I don't know, something like that. The problem, just as it was in the early days of mode-locked lasers, is to remove the chirp well. So I didn't say that before, but the problem is to remove the chirp well. Largely, the best thing that people do so far is simply pass the pulse through a metal filter, and the metal filter tends to give you the appropriate dispersion to allow the pulse to compress. I think the current state of the art is 67 attoseconds. So that tells you that everybody's struggling for the last moment. So 67 doesn't make sense. You could say 70 or 65 attoseconds. And it's done by Zhenghu Cheng's group in Florida State, University of Central Florida. Okay, so that's the basic idea of attoseconds, and you see many of the characteristics right there. I also said that there's a quantum mechanical way of looking at this. And, well, this is just an in your fingers picture of quantum mechanics. This is a way you can think about that quantum mechanical picture, that we have this electron bound to the atom. The electron can tunnel, creating a wave packet in the continuum, and of course a portion of the wave function stays behind. This is quantum mechanics. The wave packet propagates in the continuum. It's by no means as clean as this. I'm looking at sort of particular trajectory and saying how it looks, and I'm following that trajectory over all time in one photograph. So I don't mean to say that this is a realistic picture even, but I think it catches the essence. And so this electron goes over a path and comes back, overlaps the wave function from which it left, creating an interferometer from the molecule's electrons. Two parts of the same wave function, you must add them to get the total wave function. You can modify or you can manipulate this interferometer by using a number of different things. For example, there's no reason why you can't add to the fundamental, which is responsible for creating the interferometer, a weak second color. Second harmonic is what I used, and largely I will use that all the way through this talk as well. And that allows you to move the arms of the interferometer. There will be some phase of the second harmonic relative to the fundamental that will just optimize this trajectory, adding phase to this trajectory. If you're doing harmonics, this next trajectory, or the next half cycle, where the electron goes the other way, the second harmonic will decrease the phase. Adding action, decrease, taking away action. and therefore unbalance the interferometer, creating even harmonics in the present, or mixing in, if you wish to think of it that way, some of the second harmonic photon. You can bring the second color in at an angle and ensure that the recollision electron comes back at an angle, and that's also an interesting thing to do. I'm going to talk about taking the initial wave function and manipulating it as well. So that's not possible for a hydrogen atom, but if you were to think of a molecule, the orbital is stuck to the molecule, and as I rotate the molecule, the orbital rotates with it. So it gives me control over the wave function here, and I can manipulate it, and it's in some sense like manipulating an arm of the interferometer. I mean, I don't know if you buy that or not, but I think you can think of it that way. So here is the degree of an alignment that we can get for a molecule. People can do better than this. This starts out as a gas phase, nitrogen molecule, randomly aligned in space, and we come along with an intense laser pulse whose purpose is simply to create this alignment, intense but non-ionizing. The molecules feel a torque towards alignment. As long as the laser pulse is on, you create a rotational wave packet, and the laser pulse is short, so you turn it off when all molecules are aligned, and you've got a distribution something like this. In this case, the polarization was here. And that distribution will revive according to quantum mechanical rules periodically, depending on the level spacing of the molecule, but we can predict it completely. So that's a way to get an aligned distribution that you control with your laser polarization, something that we can control easily in the lab. So this is the interferometer, and I'm going to be using this for most of the rest of the talk. I talked about how to read the interferometer. This is the quantum mechanical view of the electron coming back and recombining, or it's the way I like to think of it. Electron coming back and recombining is just fine. There's nothing wrong with that. I like to look at it in this more picturesque view. The recollision electron comes back. The original orbital from which it came, sketched in the last figure, is shown here. And the superposition is actually what's really shown of the two of these, the wave function coming back and the orbital. And so you see that superposition, which distorts the total wave function from what it would be if it was just the original one. Square it, we get the probability of finding the charge on the atom or near the atom. And then you can look and see what the dipole is, and that shows the dipole. And as the electron passes, there's a dipole oscillation, and the dipole oscillation oscillates, gives you radiation. And that's the source, in this perspective, of the harmonic radiation. This is the way I like to look at it personally. That's just the dipole, oscillating dipole is the transition moment. So saying it recombines is not wrong. But what I like about it is that I can see in my fingertips why the amplitude and phase is what it is. The amplitude and phase of the recollision electron forces the phase and amplitude of this oscillating charge through the transition moment. Now I ended up, I think the last pictures I had was just one of an interferometer, and I wanted to remind you of an interferometer. We did that way back early looking at autocorrelation. We said that you could, this is an interferometric autocorrelation. And I simply wanted to make a point. I don't mean to go back to say how you measure pulses. I wanted to say we measure the electric field as a function of time from an interferometer, maybe not perfectly with an autocorrelator, but with frog, I said, we measure perfectly, and it looks very much like this. So we can measure the electric field as a function of time, amplitude and phase. I think you would agree that we could also measure the spatial properties of the beam as a function of time, amplitude and phase, as long as you allowed me to shear this interferometer in some way. We don't normally measure the spatial structure, but we could. People do. So we measure most everything about the electric field, amplitude and phase of a pulse using an interferometer, a nonlinear interferometer. So the challenge is, can we make similar measurements on molecular orbitals and molecular dynamics? So that's the issue that I set for you, is think about it over lunch hour. Think about, do you think it can be done? Do you think it can't be done? And so on. Okay? if it could be one of the new opportunities opened by extreme nonlinear optics. And so I think the last thing I said was, where do you stand on the issue of? So let me just, maybe rather than repeating it, because you'll all remember, I think it's a dramatic enough statement that you'll remember, I started to put this in a talk where I described orbitals as a result of an incident, actually. I was speaking in Vancouver at the, I think it was the VUV conference, and there was a public lecture associated. I was given a public lecture. It was a very nice occasion. And the audience was larger than this, and there was a man in the audience who got up at the end of my talk, and he was very disturbed. And he then wanted to know all kinds of things about orbitals, and he felt that it was just impossible to measure an orbital. An orbital didn't exist, and anybody who said they measured an orbital was a charlatan. And as a matter of fact, after I left, he wrote a letter to the president of National Research Council saying that a person like me should not be on the staff of a place like the National Research Council. So I decided maybe I better be careful. And I put this kind of a slide in, and I think it's useful because I think that I should say why people think this is not possible to do. Is it possible to measure an orbital? Is it not possible to measure an orbital? So you thought about it over lunch. Maybe you didn't. Think about it as I give you the talk and see what you think. Okay? So I didn't get fired, fortunately, or anything like that. And I don't know what happened to the man. I don't know if he came to terms with it or not. But I've given talks on this in the chemistry departments at Harvard and Yale and lots of places. And they all accept it, except this man. But it's a... So... It's like, well, maybe, but I'm not an expert on orbitals. I must say, I'm not an expert, so. Pardon? This could lie at the heart of the controversy. There are many ways to define an orbital. So I will tell you what we measure at the end, and chemists maybe define it somewhat differently, and that may be some of the problem. So an orbital is what an effective, I think you might say, an effective electron goes through. But it's not a real electron. Electrons are interchanging and things like that. I like the definition of what we measure as a Dyson orbital. That's a clean, clear, and you really know what it is. So can I wait till the end to tell you what we measure? And chemists... we know I was not permitted to ask a question. At the middle of the talk, you're not supposed to ask questions, Bob. That's right. Absolutely. You're irresponsible. Okay, so now I want to talk about what I'm going to do. I'm going to talk to you about orbital tomography, measuring an orbital, photochemical dynamics, and then is there any chance to extend to the solid phase? So tomographic imaging. We're going to tomographically image a nitrogen orbital. It's going to be an interferometric-like, but you could think of it as interferometry if you wish. But when we did it, we first called it tomographic image. So I want you to sit there and look at it and you think about how you do a tomographic image in medical, because we're going to use exactly the same algorithm. Okay, for a tomographic image in medical physics, x-rays or whatever, you take a beam, you shine it this way, this way, this way, this way, and you get multiple projections through the system, and then you use these multiple projections, that information, to reconstruct the three-dimensional structure of the patient. Okay, so we're going to do much the same kind of thing. So we need a way to align a patient, our molecular patient, in the machine that we're going to do it. So this is what I described to you just a minute ago before. We take the molecules that we wish to study, in this case nitrogen. We apply an intense but non-ionizing laser field. So let's say the field is pointing in the horizontal direction, as it is for this image. The molecules that are randomly aligned, many of them see a torque towards alignment. You can think about the molecule sitting there, the laser field, as long as there's no resonance close by, pulling, biasing the electrons inside, inducing a dipole, and that dipole interacts with the field and causes the molecule, puts a torque on the molecule. And any molecule, no matter what its orientation, as long as it's 90 degrees, will move towards alignment. So we can take a random distribution and align it. It's very much like a pendular problem. We're like as if we're taking a whole set of random pendula and turning on gravity and then turning it off again. So as you turn on gravity, all of a sudden they start to fall. And since all pendula meet at the center, as long as their angle's not too great, it's really like that. And then you turn off gravity. So you can't do that with gravity, but you can do it with a pulse. So that's a way to align molecules, and they go through now easily predicted alignment dynamics. So right away, you go through an alignment, but then after a delay that's determined by the rotational constants of the nitrogen, in this case 8 picoseconds, you go through an alignment dynamics, which is first an anti-alignment, and then an alignment again. Maybe it's alignment and anti-alignment. I think it goes backwards. Yeah, it's alignment and anti-alignment. And so we choose this time afterwards to do an experiment. Our laser pulse that's done the alignment, it's long gone. The experiment can be done cleanly. We don't have to worry about overlapping two pulses. And so that's the way we align it, and we simply choose the distribution at the time we know the alignment. Changing the polarization of the laser changes the orientation of the patient. Okay, so now just to make sure that we're all on the same page, here's an illustration done by an artist, so don't expect too much, of the nitrogen molecule orbital. The nitrogen molecule orbital is shown here. There's 3 lobes. They have opposite phases, which are represented by the color and the plus and minus. Of course, we don't know what's plus and minus. That doesn't make sense. It's like a real absolute phase in optics. We don't know. And then here is the electron being pulled away and driven back, and now it's overlapping. And she's caught the moment when the wavelength of the recolliding electron is more or less the structure size wavelength. So you can sit there and think about how the interference looks like as this washes by, and how it looked like as the red washed by before it, and as the blue part washes by afterwards. And this oscillation, that interference, is going to give us the radiation that we're going to see. So that's one alignment. Now think in your mind, if I rotate this through 90 degrees and you look at the interference again. So we could all sort of do interference. In our mind, think how the interference is going to look. It's going to be very different. I think we would all agree. And so the radiation pattern that we see as a result of this should be very different. So it's, in a way, it's this interferometry again. So this is only there, but I think I've said all of this. We can align to a whole set of angles. We're going to take 19 projections, and you can see how well we can align. This is done by Coulomb explosion. I won't describe the actual measurement of this alignment distribution. As I said, we're not by any chance the best aligners in the world. People can do much better. But let me make sure that we all understand the probability of finding a molecule in this direction is determined by where you go out to the radius. The probability of finding it this direction is determined. So you can see that we have sort of 5-to-1 ratio, parallel versus perpendicular. Okay, and we can do that at any angle. So here's the experiment. So this is the tomographic experiment. We have a pump pulse, whose purpose you know. It's a 60 femtosecond pulse. It's stretched a little bit, chirped. We all know about chirp. Chirped a little bit, so it's longer. It's 60 femtoseconds. And that's just long enough for the molecule to get down and sort of align up to gravity. And then we turn it off. Its intensity is 5 times 10 to the 13. Strong, but not ionizing. We see no harmonic radiation because of the pump pulse. So its purpose is just to align. The beam is small, so in the far field it's large, just the F number of the optics. So we align all molecules in the distribution in the area that we're going to probe, and that's the start. The polarization can be changed. Then we come with the probe pulse. We keep the probe pulse polarization fixed because of possible polarization sensitivity elsewhere. Okay, now the probe pulse is 30 femtoseconds long, 1.5 times 10 to the 14. I told you this is where ionization is really good, around 10 to the 14. And nitrogen, this is a nice intensity to be doing experiments at. The harmonics are created. They go through a slit grading onto a microchannel plate where they're imaged. So this is, you saw this one, so this is actually not from the experiment. This is kind of what everything looks like. A set of harmonics stretching from 15, in this case out to harmonic 39, from 23 eV up to about 60 electron volts. Okay? This experiment we did quite a while ago. Now we could do it at 1.8 microns, and it would stretch out here to 300 electron volts. We'd have better resolution. So here is the harmonic spectrum that we measure. It's not exactly the harmonic spectrum, but it's really close. So first let me say what's here. Here is the harmonic number, or wavelength if you wish, starting at harmonic 17 and I'm ending at harmonic 43. This is the harmonic intensity that you see in relative units. And this is for a whole set of orientations going at 5-degree intervals between 0 and 90 degrees. I don't think you want to look at any one of them, but what you want to look at is the difference in the distribution that you see as you make this angle. But then how would you expect it not to be different when you think about how different that interference could be? So this is the basic information. I said it's the raw data, but it's not exactly the raw data. We have one issue that we have to calibrate. So it's important to know what's the probability of the electron recollision to have a particular energy of recolliding electron, or particular K vector of recolliding electron. And that we don't know so easily directly from the experiment. So what we have done is we took an atom that ionizes almost exactly in the same way, something that we say we'll know as a reference. We took argon. Many experiments have looked at argon versus nitrogen. They're almost identical. And we said, we'll use argon to calibrate this. A was back in the equation earlier, if you happen to look at it. It was color-coded way back in the last lecture. So this is actually a ratio of argon to nitrogen, and we assume we know the orbital of argon, not and nitrogen we're going to determine. So it's really an issue of determining that. It could be, I think, determined all experimentally, but we did not. We used this ratio technique. And I think everybody that's done this kind of experiment since has done a ratio technique. So here is the results of the measurement. So we take that data, put it in a tomographic algorithm, and just reconstruct. So here's the experiment. It comes from 19 projections, 5-degree integrals, using tomographic methods. Here's the experiment. The color code tells you the different phases between the different lobes. Those are measured. Can you imagine the electron winding its way around the orbital? And it would be very different if we had 3 equal lobes, which would be hard to imagine, but it would be very different. So there it is. You can see them right there. This is a 1-electron Hartree-Fock calculation, so it looks significantly different. But eventually, about a year or two later, Brabitz and some people at NRC did a much more careful multi-electron calculation. And they said, okay, but you only go to 60 eV, so you got limited resolution. So let's put in the resolution limit of your tomographic image. And so they put in that resolution limit, and here's what they constructed. I think the overlap or the agreement is really good. So that's the agreement. Of course, there are rings around here. And so what are the origin of the rings? Well, there's two possible origins. I guess the limits of the energy are taken into consideration here. But the main error I think we make is that we assume that the electron comes back as a plane wave. That allows us to use tomographic algorithms, Fourier transforms and things like that. And in practice, the electron is coming back to an ion and it's pulled in, it's a Coulomb wave. And so the plane wave approximation is not perfect, it has some flaws. But in some ways, the way I won't try to say any more than that. So I think that's the origin of the radiation out here, and then somebody would have to go at it mathematically to do it better if you wanted to solve that issue. But we see the wave function, not the wave function squared. We see electrons, amplitude, and phase. And that's, so I don't know if you're comfortable with it. So what have we measured? So this is Bob's question. What have we really done? So far, I've talked about everything in single electron language. However, and that's the way we thought of this experiment, I must say, when we did the experiment. We're a bunch of physicists. We didn't think about all these multi-electron effects. So what have we done? We've taken an n-electron molecular wave function. And we've constructed an n-1, that is an ion, plus an electron in the continuum. So that's the electron going out here. It's the n-1 plus the electron and the n-electron. And so now we bring it back and recombine. And so we see the difference between the n and the n-1 electron molecular wave functions. And that's how the Dyson orbital is defined, the difference between the two. So we see the Dyson orbital. There's apparently a number of ways to define orbitals. We see the Dyson orbital. But this is what you would, very close to what you would find in a textbook calculation in chemistry book. So it's the Dyson orbital, the difference between the n and the n-1 relaxed wave functions. So now, so that's the orbital imaging. The structure of that, let me go back before I go to the next part. The whole structure of this spectrum is determined by the structure of the orbital, right? The whole structure of how it looks is determined by the structure of the orbital. Oops, I'm going the wrong way. What we're reconstructing is the orbital that we ionized. Tunneling selected the orbital. So HOMO orbital. And at the time we did this, we saw that we thought there was no other option. And so there is a chance that some other, well, we know that there's another option now. And that's what I'm going to talk about next. Oh, going the wrong way. Before I do it, I want to stop for a second and make a connection with other forms of spectroscopy. So what one does in photoelectron spectroscopy is you take a XUV pulse in, you photoionize an atom or a system, you create a photoelectron replica with encoded molecular information inside encoded molecular information. You make a replica of the XUV pulse, but with some encoded molecular information. That's what we talked about in the street camera. You selected so the molecular information is boring and you can understand the XUV pulse. So that's photoionization, and many people use photoionization as a form of spectroscopy. What have we done? We've done something somewhat different. We've made a photon replica with encoded molecular information of the recollision electron pulse. So we've done photoionization in reverse. We've made the electron, we think we understand it, we bring it back, and we make the reverse process. Okay? So this is very closely related to photoionization. So notable differences. High harmonics measure photons, which is great. We can easily measure photons. They actually you can even do coherent experiments, as you'll see very soon. Phase matching, not space charge, provides the limit. So in the photoelectron, space charge we limit you to a few electrons per shot. In high harmonics, we can see, I make this up, 10 to the 8 photons per shot. So we don't have space charge limits. The electron is barely out in the continuum before it's back again. It doesn't know about anything else. It can be highly multiplex. Every frequency is created once, right? The electron wave packet has many, many different energies all at once. So it's highly multiplexed. In photoelectron spectroscopy, you would tune through all of these frequencies. It would take you days and days to do what we can do in a few shots. High harmonics can borrow methods from coherent optics because the electron information is transferred to the light where we have access to all the coherent techniques of optics. So again, you'll see that in a few minutes. We'll use it. And optical methods can remove space-time averaging. And in some ways you saw that because we could tell you fully about the space-time structure of a pulse that I did last time. However, it's not all perfect. However, there's a strong laser field constantly present in high harmonic spectroscopy. And so you have to be sure that does not affect the experiment. I say, although not much larger than in most femtosecond experiments, because femtosecond experiments always have a problem, but I'll come to that in a minute. Energy conservation can't be used in high harmonic spectroscopy to know what you did. You have to find another way. I'll come to that in a few minutes too. And only weakly bound orbitals are visible, although probably you can get around that. So those are the comparisons between photoelectron spectroscopy and high harmonic spectroscopy. Yet I think that high harmonic spectroscopy is a powerful technique that will grow. So now I want to make a jump, and I want to go from statics to dynamics. So the first thing I want to talk about is back to tunneling. Back to tunneling. So there's a sort of a question. How can an attosecond electron wave packet be created? So one way is to take an attosecond pulse and transfer population to a superposition of states, and that superposition of states will look like the attosecond pulse in the first place, and it will evolve. It's just like I said before, you can transfer information by photoexcitation coherently. So that's one way. But we don't have so many photons. It isn't so easy to do that, and it's awfully hard to do experiments. So another way is to use tunneling itself. Now, it seems strange because I sort of implied to you, and we all know about tunneling, and tunneling is exponentially sensitive to the barrier through which the electron tunnels. So how can I possibly ever create an attosecond wave packet? So that takes us back to this equation. If you think about this equation, that gives you the ionization rate for a hydrogen-like atom. Remember, everything was sort of in atomic units against a reference that was natural, so the electric field is related to the atomic field and things like that. But you don't have to look at all of that. All I want to say is when your ionization rate is low, as you would have in any DC experiment, like in an STM or something like that, when the ionization rate is low, then this exponent is a very small number, minus, exponents minus e to the minus 30, e to the minus 40, and a small change in EI will make, is highly leveraged against, so it makes almost no difference, essentially. However, if you force the ionization rate very fast, so that your ionization must be over in the duration of pulse, 50 femtoseconds, then you're really forced to push this ionization, this term, up to be much larger. The exponent is only, say, minus 10. And now the leverage is weakened, and lower orbitals can relatively easily contribute. In other words, a 2 or 3 eV penalty in IP is hugely important when the ionization rate is low, but it's not so important when the ionization rate is very, very, very high. It's only the structure of an exponent. It's not saying anything that's not in the mathematics there. Nothing new about tunneling. It's just a bias that we and this whole field brought into the community, into it in the first stages. So the experiment that I did in nitrogen, we didn't assume any other orbital could ionize. We now know that it can, and it's amazing that it didn't contaminate the experiment. So I want to talk about the ionization of CO2 as an example of what it is. So here's a CO2 orbital. This is the highest occupied orbital. It's got the 3 lobes. You can imagine it, positive, negative, are the blue and the red. That's the structure. This is the next one lower, and this is the next one lower still. So HOMO, HOMO minus 1, HOMO minus 2, highest occupied molecular orbital, HOMO, HOMO minus 1, down 1, HOMO minus 2, down 2. This one's about 4 eV away from the other. Now you remember about tunneling. Tunneling has got this filter that lets the wave function sneak through if it can get through the filter. And so if you line the molecule up like this, and this is like a little filter that's trying to, there's not much wave function on axis, so it's awfully hard for this orbital to sneak through, and the HOMO to ionize at that angle. Similarly with this, but this one has no problem, right? It can easily, it's got a big lobe there, lots of momentum wave function. It can get out through the center of this thin filter. I like to think of it as like bringing a beam into an undersized spatial filter. It's like Bob's wave. Remember, Bob had a way of picking out orbital angular momentum beams and things like that by getting into a mode. It's almost the same issue. Okay. So here's the probability of ionization as a function of angle calculated for each of those orbitals. You can see that the ionization probability is suppressed on axis, and not suppressed on axis. So now we have 2 things that say that this lower orbital might play a role. First, this very fast ionization. It doesn't have such a penalty. And then it has the right structure to get through the hole. So, in fact, that's what you see. We start out with CO2. CO2 can ionize through the HOMO, or it can ionize through the HOMO -1, creating an electron wave packet that's out and back again and returns to one or the other. So 2 contributions to the harmonic radiation. 2 contributions can always interfere, and if that's the case, we should see this show up in the interference between the 2 in the spectrum. In fact, that kind of interference is seen. So here is the spectrum we see for the radiation created for a molecule of CO2 aligned. You know how we align them now? Aligned in a distribution. So this is the molecular alignment angle right there. Here's the harmonic number going back, and this is the intensity. So you can see now this change, and you can see a structure, a minimum and a maximum. And that minimum and maximum could be the structure of the orbital, that the electron comes back and there happens to be a minimum, or it could be because of this interference. But if it's a minimum because of the structure, it will never move. The structure is the structure. If it's a minimum because of the interference, as we change the intensity of the light, the interference will change, or the wavelength or whatever. We're going to change the intensity in this experiment, and we will see that interference change. And so now we're watching a wave packet launched by tunneling in the molecule. Okay, so this is a calculation for transition moments, molecular alignment, harmonic number, and intensity and phase here that go into it. I won't spend much time on it. And here's a calculation for where that interference should occur at different intensities of light, from 0.56 times 10 to the 14 up to 2 times 10 to the 14. And here's an experimental results. So they fit almost exactly one on top of the other. So we are creating electrons from 2 orbitals. It doesn't know which one it comes from, so out goes the electron, it comes back, and it creates this harmonic emission that interferes. We've launched a wave packet by populating these 2, and this is a whole wave packet, and that's what it looks like over the time of the experiment. So the simplicity of CO2 allows us to uncover whole wave packets that are launched by electron tunneling. So isn't it amazing? Again, attosecond phenomena are described by tunneling. I said this is amazing that Keldysh could have said it. And isn't it amazing that attosecond electron wave packets are also created by tunneling? Perhaps this will be ubiquitous in solids and in molecules. So DC process creates attosecond motion. But of course you need this correlated electron to come back and time it perfectly. If you didn't know when it occurs, you would have no chance of seeing it. It's only because this electron comes back and probes itself that allows you to see it. Okay, now I want to show you chemical dynamics. This is a very beautiful experiment, I think. And so I think you will like it, even though I know you're not chemists, so I don't think you are. So I want to tell you about chemical dynamics, but this is a physicist. I'm a physicist. I don't know anything about molecules. I'm hard-pressed to tell the name of anything except a diatomic. We're going to take bromine as the example. So bromine is really simple, and for me it's even simpler than you can imagine. So we start with bromine in its ground state, there it is, and we're going to photoexcite it to a directly dissociated excited state. So that's very convenient because it takes 400 nanometers to do the excitation. That just means doubling our 800 nanometer pulse. It's very convenient also because bromine is kind of heavy, and so nothing happens too fast in bromine, so it's not a heroically fast experiment. But immediately you have a problem. This is true for every short pulse experiment that you do, no matter what. You have to, and we don't even think about it, because we sort of know how to get around it under normal circumstances. If you want to move transfer population from one to the other, then you need a certain number of photons. And with a short pulse, you haven't got so many, so to get some photons, you need to push the intensity. But you got this short pulse, you're not even in resonance very much, and so you're really driven to high intensity before you can move much population. But as soon as you're at high intensity, there's no reason for the population to stop at the level you wish. You can keep going. So in order to control the transfer of population with a short pulse, at any short pulse experiment, this is true everywhere, in any short pulse experiment, you really have to keep the intensity low. So we started out this experiment by doing a first experiment to make sure we understood how much intensity, how much population we could transfer reasonably without losing control of the process. So 10% at best, 5 to 10%. So it was sort of discouraging when we got to that point, because you immediately say, how can we identify the signal of a few dissociating molecules in the presence of lots of normally dissociating molecules? So conventionally, in everything that we do, we find a spectroscopic way to do it. So in ordinary femtochemistry, you just look and say, let's imagine you let a photoelectron go. If you go from the ground state, the photoelectron has got less energy than if you go from an excited state. So you can see an awful lot by energy resolution, but harmonics are harmonics. We can't do anything, or an attosecond pulse, you would never be able to do that. So this is just not available for high harmonic spectroscopy. It's just not available in either case, high harmonics or attoseconds. So how can we possibly get around it? I'm going to skip that for a moment. So we started the experiment no matter what, even though it was discouraging at that point. And so what do we see immediately? So here is time delay between a pump and a probe. There's 0. And that's, you see a whole series of them for harmonic 13, 15, 17, 19, 21, and 23. And you see 2 curves. The blue ones are the odd harmonics, which we're used to thinking about. The red ones are the even harmonics. You remember they come when you can mix in a second harmonic photon. And the only way you can mix in a second harmonic photon is have them there simultaneously, as I showed you earlier, and you manipulate the trajectory. So these ones just tell you when you got the pulse overlap, and so other than to tell you where 0 is, you can ignore them, okay? But when you look at the blue ones, you see that, my goodness, even though we only excited a few of the population, where they should be less bound, and so they should ionize more, and you might have expected the signal to go up, we see it go down, and sometimes it goes down a lot. It goes down 50% or more. So, well, of course, what happens is we have a homodyne detection system. We are creating harmonics from both the ground state and from the dissociating molecule. Every time we fire the laser, some of the molecules in the ground state ionize, come back, recombine, create harmonics. And some of the molecules, depending on the time delay, let's imagine it was here, they ionize, come out, and recombine and create harmonics. And so we have 2 sources of the same color. One, a fixed source that doesn't change as a function of time delay. It's almost ideal. It's exactly what you want. It's like in a radio, right? You have a local oscillator against which you pick up a weak signal of the dissociating molecule. That's why it's so small, okay? So a very large time-dependent signal with very small excitation. So the seeming disadvantage of high harmonics becomes an advantage. The coherence saves us. It really allows us to do it. However, we have amplitude and phase mixed in this signal, and so how do we know what's the amplitude and how do we know what's the phase? So there we reach out to perturbative nonlinear optics. In ordinary nonlinear optics, you often set up grating experiments to do this kind of thing. So we said, why not excite the molecule with 2 pulses coming in at an angle? Okay, so there they are coming in at an angle. They interfere, creating lines of constructive and destructive interference. You can see them maybe there. I don't know if you can see them in the back or not. I can see them up here, but I'm not sure you can. But you can imagine what it is. It's a whole set of lines of constructive and destructive interference. Where there's constructive interference, molecules are separating. Where there's destructive interference, nothing is happening. So I have made a grating of dissociating molecules. In that grating of dissociating molecules, I can come with my 800 nanometer pulse and create high harmonic radiation. Of course, I see a grating, I see a diffracted pattern, 0 order and 1st order. Again, I don't know if you can see it, but therefore, for every frequency, I have a 0 order signal and a 1st order signal. amplitude and phase behave differently for the 0 order and the 1st order. So we have 2 equations, 2 unknowns. I personally like to think of it that it's phase that's most important for the diffraction, so the 1st order's phase. But there's an equation, 2 equations, 2 unknowns, amplitude and phase. So we can separate amplitude and phase. This becomes a fully coherent spectroscopy. At every time delay, we relate the dynamic signal to a fixed signal, the local oscillator, from the unexcited molecule. So here are the results, and I want to interpret the results now for a minute. So here's the amplitude of the transition moment to the continuum, right? The transition moment is the important thing. And here's the amplitude for dissociating the molecule in such a way that the atoms are coming apart like this, and the laser field is pulling the electron like this. So I think the illustration is transparent. And here it is for when I'm associating them perpendicular, and you might expect some differences. So if you look at this, you will see it. This is the phase difference between the excited state and the ground state fixed. And there's maybe some differences, but they're not nearly so dramatic as the amplitude differences are. I want to zero in on 2 aspects of this figure. One aspect are these dips. They're very prominent. They all occur early. Let's try to look at them by bringing them to the same 0. So just scaling them so they're the same. Here they are. This is scaled version of that. Excuse me. So you can see now that the minimum is moving in an orderly fashion to later and later delays. So what's the cause of that? In fact, we see it in both cases, both molecules, both cases. So what's the cause of this? It's kind of an interesting phenomenon. Why would it possibly be the case? Well, the electron that's creating the harmonics can, I think I got a figure, so let me just jump to the next. I think I got a figure that shows it. The electron that's creating the harmonics can come from one of these atoms that's now dissociating or another atom that's now dissociating. But they're still phase coherent. They were one molecule not long ago. And so the source, when the electron comes back, the source from each atom is 180 degrees out of phase when they're separated by a wavelength and a half of the electron, not of the photon, but of the electron. And so that destructive interference leads to the minimum. So we can calculate it. It's easy, right? We know what the electron wavelength is. It's trivial to do it. And you can calculate the dissociation of the molecule. And so here you see the dissociation of the molecule as it would be seen for harmonics or wavelengths. It's different. And here is the experimental results coming from that 3/2 wavelength interference. In other words, the electron is interfering and measuring the distance between the atoms. We're using the electron, just like I said we could, but through the harmonic radiation. So it's very beautiful, and well, you watch the atom separate with high precision, of course, because the electron allows you to do it. The 5/2, interestingly enough, is not, you can't see it. So whether exactly why is an interesting issue, and I don't think I can answer it well. So that's one thing out of the figure. The second thing out of the figure is also important, and I want you to remember it. So if you look at this case here, that is where the atoms are separating in the direction of the electrons going, you can see that the amplitude is very badly disrupted for a while. And then all of a sudden it settles down. And it's true for all harmonics, so we see it all of them. So what's the cause of that? Well, the electron could be created on this molecule. Maybe it was in this one, so we don't lose all signal. But it could be created in this molecule. And if it does, until the atom gets far enough away, the electron can cast a shadow, can break its phase, can become a source of dephasing in the problem. And so when the electron comes back, it's either shadowed, so you see less of it, or it's dephased, either way. And so you see the disruption until the atoms move apart, and then everything settles down. So it's almost like looking at the separation of the atoms through pushing this electron out and back again and getting it to report. Okay, so that's the second thing you see from this result. So I like to say that this is a fully coherent photoelectron-like spectroscopy. That is, we now measure the amplitude. Right now, by now we have measured the amplitude and phase of the transition moment compared to the ground state. We've rotated the molecule, so compared to the ground state at every orientation. And then we've taken a molecule in the ground state and rotated it and done it with respect to an atom, a fixed atom. So now we know amplitude and phase at all orientations and all frequencies relative to a fixed atom. So I think that's the maximum you can know about a problem. We started out this to try to do a tomographic movie. As you can imagine, it might be interesting to do. But of course, the multiple orbitals make it much more difficult to do this. And especially as levels are coming together, it seemed like maybe it wasn't such a good idea as it seemed when we started the experiment. However, no matter what, this is amplitude and phase of the transition moment, everything you can know about the system. Now, I'll stop for a break, but maybe I will just do this because I'm only going to spend a moment on it. It's not a chemistry audience, but I want to just show you that you can move this one more step. And I'm probably going to finish the whole, well, maybe this is a good place to stop because I will finish early, I think, in the whole. I know I'm going to run out of view graphs before I run out of time, but that's probably just as well because 5.5 hours is a long time. So why don't we take 10 minutes? I'll go ahead. Okay, so I'm going to just spend a few minutes on going from diatomics to triatomics, and then I want to spend about 15 minutes on solids. So I'll come right back to the issue, not in quantum well, but it's close enough to it that I think you'll be interested in it. So we decided to do something that would capture chemists' attention again, but stay small. And so we thought it would be interesting to go to a molecule like NO2. It has the advantage, like bromine, that 400 nanometers will excite you from the ground state of the molecule to the B state of the molecule. And in the B state of the molecule bends even more to a smaller angle. And as it bends, the energy levels shift, and there's an exchange or a crossing of the energy levels where the electron can make a transition from one energy level to the other and go down into the ground state. So to chemists, these are extremely important. They drive a great deal of chemistry. So chemists think about these all the time, and these are called conical intersections. This is only a 2D picture, but conical intersections are lines or planes that occur in all molecules, all large molecules. So the idea was to excite the molecule and then have it go through the conical intersection and see what we could observe. So now we're going to bring the tools, amplitude and phase, together to look at this and see if we can see the conical intersection and so on. So again, the experiment's the same as before. You understand how it's done. Two beams come in, they cause a grating. The grating is used for the harmonic radiation. The harmonic radiation gives you diffracted radiation out here, and so we look at it and we get the amplitude and phase from this diffracted radiation. So here is the results. For m equals 0, that's the 0 order signal. M equals 1 is the first order signal. So this is just the raw experimental results. And since we have 400 nanometer light, 400 nanometer is right close to the dissociation threshold of nitrogen. So we can go at 397, or we can go at 407 by just misaligning the doubling crystal. And we can see the molecule dissociate over a few picoseconds. But you don't expect anything very fast in a triatomic molecule. The energy is everywhere, and it takes a long time for it to find its way into the appropriate bond. This is, I think, widely viewed to be statistical behavior, and I think it probably is. Okay, so, and at 407, we see that it doesn't dissociate, and that's just so you see no long-term dynamics. So that's not so interesting because there's nothing to see on a fast time scale. But if we were to go in and zero in on much shorter time scales, so now the time delay instead of being picoseconds is in femtoseconds, and here is the amplitude and phase, or the m equals 0, m equals 1. It's not quite amplitude and phase. And you can see on the diffracted radiation an oscillation, and there's an oscillation on different harmonics that we see. So that oscillation is the oscillation of the system as it goes through this conical intersection. It's actually, you're looking at the vibrational motion as it's trying to go through and make its decisions and so on. And it's been calculated before. And so here is the results of the calculation. It was done by Vince McCoy's group in Caltech. And that's the calculation. And here's what we see for the experiment. So we see the system as it goes through the conical intersection. We're sensitive to changes in electronic structure because of the interference, and we see that change because we're sensitive to change in the electronic structure. So that's as far as we've gone with the experiment, but we observe a system going through a conical intersection. So I say that, just to conclude this part of it then, high harmonic spectroscopy is a technology by electrons, for electrons, for measurement and control. It's sensitive to electronic structure. I didn't emphasize, but it's sensitive to IP changes. That's why the phase was there compared to the local oscillator in all cases. And it's compatible with chemical dynamics of small molecules to deal with your issue. And large molecules remain an open question, I think. So now I want to go on to the very last part of my talk. So no matter what, I wanted to do this. So does recollision have any place in condensed phase physics? That's the last question I want to ask. So I told you my bias that is there right from the beginning, and I think most of the community had that bias. Nobody really paid much attention to the people who were talking about recollision in solids. They said they were few and far between, but they did exist. It's kind of funny because Keldysh treated gases and solids on an equal footing. I told you that Keldysh, although he never really pulled it out, and maybe I don't know how much he really consciously thought about it, he had the electron oscillating, right? UP is an oscillating energy. He had it oscillating in solids. Maybe he didn't take it quite seriously in solids. I don't know. I never asked him. But he treated it together. And tunneling is still used to describe dielectric breakdown in laser machining and things like that. But otherwise, this field diverged after Keldysh, went off to machining in solids, went off to high harmonics and attoseconds in gases. So can we bring them back together? And then if we're going to bring them back together, the big issue is, can the electron go out over this trajectory and come back and maintain its phase relationship? So when it comes back, there's a phase to the harmonic radiation that it would create. So this is just stating what I said before. It started with Keldysh, and this system diverged. People went off to do all kinds of laser machining, and people went off to do high harmonics and attoseconds. So over the last couple of years, a few papers have come out that really make you take a look at this much more seriously. Here's one. It's using terahertz high harmonic generation, and it interprets what happens in the solid as a block oscillation. Now, I don't know how much you're familiar with block oscillations, but if you're not, I'm going to just hold off for two view graphs, and I'll tell you a little bit about a block oscillation. So this is one paper. To me, much more important was this paper. It was earlier. It was a paper that came from Lou DeMoro's group, one of the people, and Pierre Agostini, two major people in high harmonic generation in gases. And David Rees, and I knew all three of them. And I met rapidly Shambhu Gamir, who's now at Stanford, and I spoke to him deeply and many times about this experiment. And so this seemed very interesting. They took zinc oxide. Its band gap is 3.3 eV. They used a mid-infrared laser, in that case about 3.3 microns, if I remember. And they saw harmonics coming from a solid, and here are the harmonics on an exponential scale, so they're not so bad as they look here. Here are the harmonics that you see under two different, this is a higher intensity than this one is. So these seem to be real harmonics like the harmonics you see in gases. So what is the cause of these harmonics? So I would like to now spend a moment and try to tell you about how to look at it. So I want to reinterpret what I've done in gases in solid state language first. Well, I'll immediately jump back to solid state. So in solid state language, we've been talking about a photoionization, creating an electron in the continuum. So here is the band structure for this conduction band of the electron in the continuum. Of course, we know the mass is constant, so it's a parabolic band and all that sort of thing. But if I put it in solid state language, there's the momentum of the electron, and there's the energy of the electron. We don't usually think of it that way. We think of it in real space, but you could think of it in momentum space. Now the ion is created, it's a charged particle, it sees the field also. Its momentum is equally accelerated, but it's flat, that is, the energy doesn't change as it gains this momentum. So there's what happens for an atom. And now we're in momentum space, not in physical space. Of course, the electron comes back to the ion in physical space, but where that is in momentum space, well, that's what we've been talking about. We've been talking about the recollision energy. So on this figure, it's an electron coming back and making a transition somewhere out there when it came together in physical space. So, and we've been worrying about the transition moment, the two-band transition moment, I will say in solid state language, the electron making a transition from the continuum to the ground state, or making a transition from the conduction to the valence band in solid state language. That's what we've been worrying about. There was another source of harmonics which I never commented on before, but it's known. There is another source of harmonics, and that is the current, sort of a real current that's created here. Think about what that current is. Charge times the number of electrons times the velocity. The charge is easy, it's electric charge. The velocity is easy, as long as the electron's formed, it's just going to do F equals ma like. But the number of electrons as a function of time, that's different. Number of electrons is jumping every time the field is great, that's what tunneling tells us. So it's got a step function-like behavior. Not exactly a step function, you got a 300 attosecond more or less window for ionization. So this current contains harmonic information. It's a single band current, occurs only in this single band, but it's caused by a transition from the other band. So that's there, we just didn't talk about it earlier. But that's related closely to the Bloch oscillation, that's why I wanted to come to it. Okay, now let's go back and highlight the differences that we have between this atom and the solid. Well, of course, the solid, the electron is inside a material. As the electron picks up momentum, it gets closer and closer in wavelength to the lattice. It interacts with the lattice, and the mass of the electron begins to change. It gets larger and larger, and it can get to the point where the electron wavelength is equal to the lattice spacing, and the electron can bounce back. It's a Bragg reflector for it. So there's the Bloch oscillation. It goes up, hits the edge, and bounce back, right? So this non-sinusoidal motion will create Bloch oscillation. It's actually related to then the real current. I create an electron, and now it moves in this band, so it should have both the step behavior and also this, now it's not sinusoidal, not boring, it's got this Bloch behavior. And it it's in any band, I guess it could also be in the valence band. The conduction band is what's mainly considered. So the J has harmonic content because of the band structure and the tunneling, both. The band structure because of the Bloch oscillation, the band structure even more generally because the band structure is not sinusoidal. So it doesn't even need only to bounce off, but bouncing off is the dramatic way to say it. So this is those two papers that I just showed you felt that the process was caused by Bloch oscillation. And I must say that as I talked to Gamir and David Rees, I was willing to accept this. So I had a PhD student like you, and he was interested in this problem. I didn't point him to the paper, he just found the paper himself, and he said, this is really interesting, I want to work on it a little bit. And I said, okay, but I think it's sort of understood, you know, it's not so interesting maybe. But he was interested, and he went off and he calculated the Bloch oscillation term, and it looked good. And so we all thought, okay, it's Bloch oscillation. So he went off to Thomas Brabant's, one of the prominent theorists in this area in Ottawa. And Thomas said, Giulio, do it right. So let's set up a two-band system and let's work it out. So here's the two bands they set up. And of course, it concludes all of the things we've been talking about. The electron making a transition across the band, electrons moving, harmonic emission, everything will be in there if you do it. Right. So that's the calculation they set up. And well, interestingly enough, when they did the calculation, so I was involved, but less so. They did the calculation, not me. When they did it, the calculation, and they looked at these two different terms, isolating what we called the interband, that is coming back down, like I said before, and like the recollision term and the other. The recollision or the interband term is shown in blue, and the other term is shown in red. So the single band, we call it. I mean, there's a transition between bands. So it's really where the source of the harmonics is that's being discussed. So the difference, you have to be careful here. It doesn't look like so much, but there's 4 orders of magnitude. So the difference is 4 or 5 orders of magnitude. It's huge. Of course, immediately, you see that the harmonics are really poorly formed up here, even though it's it's a huge scale. They're still not very well formed. They're nicely formed out here. And well, we decided that that's very likely to be this electron that washes in from the back and gives you complicated emission. And so we immediately thought we better put in some dephasing to get rid of that. So dephasing, instead of being a disadvantage, allowed us to get well-defined harmonics. They may not look well-defined here, but again, remember the scale. So theoretically, we required high dephasing, and we found that the emission seemed to be caused by this recollision or interband process that I described to you before. So we looked at this carefully. We began to develop an analog to the classical model, so maybe a generalized classical model. The electron and hole are created, but the electron moves with its band-corrected mass, not its free electron mass. And so we can follow its trajectory and have the electron come back and have it recombine and make predictions on what we should see. Here is such a prediction that comes out for an intensity of 0.0053 atomic units. You can tell I didn't do it. I don't think in atomic units that fast. But that's a reasonable intensity for the problem. And here is what comes out from a time-dependent solution of the two-band model, everything. And here comes out from a classical-like calculation, a trajectory calculation, just like we've done before. So then the model is indicating that the emission is caused by something that's recollision. We could go above and below. This is getting, so the electron gets up close to the edge and is about ready to bounce back. That's what that intensity is. But you see the distortion that comes from this change in mass. But you can see that it's mostly captured by the white line, which is the classical simulation. There's important for the field, because people have looked at, is what is the cutoff energy and how does it scale? And it scales the way experiments show. It's not so important to motivate it for you. Okay, so that's the theory. So now the next thing is the experiment. So we need to do an experiment to see if this is right. So you all know now what kinds of one kind of approach to do such an experiment. We said, let's bring along both fundamental and second harmonic light, like we've done many other times. And the second harmonic light will phase compared to the fundamental light, so that if it's trajectory-like, like we said, so I'm going to show the trajectory-like case first. If it's trajectory-like, there will be a phase of the fundamental that will optimize a given harmonic, creating the imbalance a given harmonic, giving you optimal second even harmonic. Right? We're looking for an imbalance in the odd harmonics, giving you an even harmonics, imbalance the interferometer. And that will change depending on the trajectory or the energy of the photons that are created, just like we've done for everything else here. We should do the same kind of experiment. So you can think of it as we've created this interferometer, and we're manipulating the interferometer, moving the arms back and forth, and we're saying, when do we get to the extreme for each trajectory of the motion? Now you can say, I've built into this experiment a bias towards recollision, but it's not true. Think of the electron going through a Bloch oscillation. And as we modify the phase of the fundamental and second harmonic, we push the electron closer to the edge of the band in one case, and we don't allow it to get quite so far to the edge of the band in the other case. So we should be able to look at both cases, and we should see a different phase relationship between the fundamental and second harmonic as a function of harmonic number for each, depending on which mechanism we have. So here's the experimental results. The intensity in the experiment is 10 to the 12 watts per square centimeter. That's why I told you Ponder motive energy for solid for this intensity earlier. The intensity in the 2 omega is 10 to the 5 times lower, but this electron is quite low mass, and so it's easily modified, and the wavelength is quite long. So it's on the order of fields that occur in ordinary semiconductors under many circumstances. And here is the map, harmonic order as a function of delay time. So here we're delaying through cycles, and here's the harmonic order. Now you can see the odd harmonics, and they're deeply overexposed, but we're not so interested in the odd harmonics here. We're interested in even harmonics because that tells us the maximum unbalance of the interferometer. So here they are between 16 and 18. Here they are between 6 and 8, 5 and 7, and so on. And you can see how they go. So there is the, well, you can look at the measurement. Let me just go over here, and this gives you the phase difference between one and the other as you optimize for each color. So this is what we measure experimentally. You can see the experimental points. The calculation, a 3D calculation from the two-band model, caused by the interband term, the recollision term, is shown in the black line below it, and the Bloch oscillation calculation is there. So we distinctly differ from the Bloch oscillation in agreement with the experiment and agreement with the calculation. So it seems very much as though this recollision occurs in solids, and that the dephasing, instead of being a disadvantage, is not so much of a disadvantage. You might lose some phase, but you don't lose it all. Just a bit like the case in the bromine atom when the bromine atoms were coming apart and one interacted with the other. Okay, so this is the experiment, and well, it looks very much like the paper will be published in Nature. It's gone through almost all reviews, and it looks very, very good. So, taking stock, we find very similar results for silicon and other semiconductors, but silicon is the most important, so we've looked quite carefully at silicon. The solids provide a medium for attosecond devices, something that we haven't had good before, so it might be interesting. We don't know yet. Harmonics are sensitive to small fields, fields on the scale of those found on electronic devices, and therefore they are possible sensors for those fields. And it probably could bring together imaging and sensing of fields. I think there are many exciting possibilities that come from these harmonics. Harmonics are very tolerant to electron dephasing. We never really explored it very much before. Maybe in the bromine atom separation, and now in these simulations and in the experiments. And we think, going back to your question, it will be possible to put do tomography, use tomographic methods, be applied to solids. They can be applied in a few different ways. We think it'll be possible to determine the band structure of a solid in place. A great deal of band structure is determined by photoelectron spectroscopy. You take the electron out, and then you look at the photoelectrons, and then you sort of manipulate the system. I'm not an expert on this, but I know that's how it's done. But wouldn't it be interesting if we could use the recollision electron and use that as the photoelectron spectroscopy in reverse? If we could do these experiments at high pressure where you can't get electrons out. We could do it under highly transient conditions where it would be no chance to do electrons. So we think that's also interesting. But we might be able to look at impurity states, orbitals of impurity states, and I think that's close to your question, put electron in a quantum well, which is a bit similar, I think. So I think that it might be possible to do such things. Maybe it will be possible to do liquid phase chemistry experiments. I think this, you could think about big molecules. What's the difference between a big molecule and the solid? The electron doesn't go very far, really. It's not as if it's going all the way across the solid. So I think this is also opened up at this point, and I see it as a very exciting new direction in this area of physics, bringing extreme nonlinear optics to condensed phase. Okay, so that's the end. I want to just give you some final overview. So I think myself, when I look at it, so I haven't tried to cover all of these things, but I've covered some of them. I think that what we've done is extend a 50-year tradition of ultrafast science. In one thing, we've improved the time resolution that's available to ultrafast science, now by 2 orders of magnitude, and we have to work on dispersion. There's many problems to solve to get the next 2, but we have a chance at least of 1 more, I think. So it's a big advance, I think. We've extended a 50-year tradition of nonlinear optics, taking it away from perturbative nonlinear optics, but in a way where it's as good and as beautiful and can be calculated as well as perturbative nonlinear optics. So I think this is it's a new direction, I think, in gases and maybe in solids, so gases and beyond. So I think we've also influenced a 100-year tradition of X-ray science. We integrate X-ray and laser physics, thereby extending, I would say, the reach of spectroscopy by orders of magnitude, by laser spectroscopy. I think this is a big advance. This is also coming in through free electron lasers, but more difficultly. So this happens naturally here. And so we've extended harmonics now in experimental systems up to, well, Andreas is extended up to 1 kilovolt. And so this is a big extension of what lasers can do. And I think we've influenced, although I haven't emphasized it here at all, some aspects of a 100-year-old tradition of collision physics. That is that we determine collisions, we time them, we label things that are formed by the laser field, by streaking, that come from collisions. And so there's a class of collision physics that we can bring time resolution to. So I wouldn't overstate this, but I think we influence collision physics, at least in the lower energies of collisions. So I want to just end by saying, here, I'm not the only one working on this, of course. This is the group standing in front of the NRC building, you know, the palace, standing in front of the palace. And this is the group as it was in the summer of 2014. And, well, people from all over the world, and I have funding from many different sources. Thank you very much.